Precipitation. So precipitation is kind of the opposite of dissolving, right? So we can look at reaction quotient. Do you remember what that is? You calculate the reaction quotient the same as you would calculate an equilibrium constant using the concentrations in the same expression, but it's not at equilibrium. Okay? So you plug in your concentrations here just like you would for KSP to calculate the Q. It's just not at equilibrium. Okay? So it's the value of the products under any conditions. So if we calculate and find out that Q is less than KSP, then we know that the solution is unsaturated. More will dissolve. If Q is equal to KSP, the solution is saturated. That's at equilibrium. As much has dissolved as will dissolve. What if K is greater than KSP? Well, that means the solution is supersaturated, which seems impossible, but it isn't. It is unstable, though, and the solid will usually precipitate out of solution. Any questions? Yeah?
But the reverse reaction would also continue, right?
Yes.
But while the reverse reaction is occurring, there's precipitate that's being formed on the product end, and that is also part of the equilibrium?
So the equilibrium is we've got the solid dissolving, and we've got ions precipitating to reform the solid. And it's going in both directions.
Okay.
And that's why if you take a saturated solution of something and you just leave it, over time, what usually happens is that the crystals change shape. The solid, which may have been just a real powdery solid to begin with, you may see large crystals grow over time. And that's because when they reprecipitate, they tend to do so in a more organized manner, and they can form really nice, beautiful crystals. So we can use Q to predict whether we're going to get a precipitation happen or not. So we identify the potential precipitate, and then we calculate Q for that compound. If Q is greater than KSP, we can expect precipitation to occur. Okay, solution containing lead-2 nitrate is mixed with one containing sodium bromide to form a solution that is 0.0600 molar in lead nitrate and 0.0158 molar in sodium bromide. Does a precipitate form in the newly mixed solution? And we're given the KSP for lead bromide. So we've got lead-2 nitrate, and that concentration is 0.0600 molar. When that dissolves, it makes lead ion and 2 nitrate ions. So just for practice, what's the concentration of the lead-2 ion? 0.060. What's the concentration of nitrate ion? Twice as much, right? Because we get 2 nitrates. So that's 2 times 0.0600. And Clarence, I think this was what you were wrestling with earlier. This is the concentration of the compound, and when we look at the concentration of the ions in that compound, then yes, we are going to multiply. But if you're looking at a molecular compound, then you're not going to do anything like that. The other one is sodium bromide, and that is 0.0158 molar. And that's got sodium ions and bromide ions. What are the concentrations of those ions? the same as the sodium bromide. So they're both going to be 0.0158. So they're giving us a big hint here that the potential precipitate here is lead bromide. If we weren't given that hint, hopefully you remember that sodium compounds are always soluble, nitrate compounds are always soluble, so sodium nitrate is never going to precipitate. It's going to be the lead and the bromide. So let's look at the equation, not for the precipitation, but for the dissolution of lead 2 bromide, because that's what KSP relates to. That makes bromide, that's not bromide, lead 2 ion and 2 bromide ions. What's the concentration of lead ion right when this solution is mixed? It's 0.06. And the bromide concentration? So, yeah, that's confusing. Is it 2 times? No, the bromide came from sodium bromide, and we were told when we mix this, the solution is 0.0158 molar in sodium bromide. So that's kind of why I did this over here before. The bromide concentration is 0.0158. When that sees the lead, now we've got a possibility for a precipitate to form. But this did not come from lead bromide. It came from sodium bromide. It came from a different source. So the concentration of this to start with is 0.0158 molar, essentially because they told us that was the concentration. Yeah?
So then if the concentration of bromide came from the other compound with the stoichiometric ratios, then it would be double, right?
Right. If we were looking at nitrate,
yeah,
we had to multiply nitrate by 2 because there were 2 nitrates in every unit of this compound. But in sodium bromide, there was only 1 of each, and so then the concentration of each is the same.
Similarly, if there was another solution of 1 mole of nitrate, then we would just use that molarity?
Yes.
As opposed to doubling it?
Right.
So it's kind of just where it came from?
It's where it came from. Okay. And so, it's very important to be able to think it through, right? Because we're going to throw questions at you that seem to come out of nowhere. And you have to use your critical thinking skills and think about it and figure it out. We need to understand what it means when we have a 0.06 molar lead nitrate solution. Well, we have 1 part lead, 2 parts nitrate. The nitrate concentration is twice as high as the lead concentration because that's how it was in the compound. So here we have concentrations for these 2. What we want to do here is we want to calculate Q. Q is calculated the same as KSP, but we're just going to use the concentrations that are there right now. We're not going to try to figure out what the equilibrium concentration is or anything. So Q is going to equal the lead concentration times the bromide concentration squared. And we're going to find the value, and then we're going to compare it to KSP. (1.5 times 10 to the minus 5). So KSP is smaller than Q. Q is larger than KSP. Right? This is 10 to the minus 6. This is 10 to the minus 5. So Q is larger. That means that the concentrations here are larger than they would be at equilibrium. Right? So if these are larger than equilibrium concentrations, what's going to happen? They're going to precipitate until the concentrations drop down to equilibrium concentrations. We could calculate that what that is, but it doesn't ask us to, so let's just not. So is it going to precipitate? Yes. Any questions? Yeah.
When Q was bigger, we were supersaturated.
Yes, it is supersaturated, but it's not going to stay that way. It's going to precipitate.
Okay.
Because it's above the solubility.
Okay.
It's unstable.
So if it's below, or so if we're just not at equilibrium, I don't really understand.
If Q is not the same as KSP, something's going to happen.
Yeah.
Either more solid would dissolve, if there was more solid to dissolve, or a precipitate will form to get rid of the extra ions. It's going to go to equilibrium. It's not, it won't stay here. Things always go to equilibrium. Does that make sense? Kind of? Any other questions?